Good evening, everyone. A very warm welcome to the Astronomical Society of Edinburgh's first meeting of the 25-26 season. I'm Neil Martin, President of the Society. This is my first in-person meeting in this role, and I'm going to use the word exciting a lot tonight, and I can tell you right now that I'm tingling. I'm hoping it's not some sort of allergic reaction. I'd like to extend an especially warm welcome to our guest speaker this evening, Professor Brad Gibson, who I'll introduce formally later. But continuing the warm welcomes, here are our latest new members who joined us over the summer break. So Stephen Berman, Chloe Clemens, Marius Evans, Jaya James, Shelley Pollock, and Mark Whitson, which brings our total membership to 207. So, are any of our friends with us this evening, our new friends, in the room or online? If so, give us a wave or hi, welcome guys. Let's welcome them. Welcome to the ASE. And now if you're joining us on Zoom, you can pop your mic on mute. Thank you very much. Okay, this evening then we have 4 topics on the agenda before we finish up with tea, coffee and chat in the room, and if you're at home you can pour yourself a drink. I'll begin with some commentary on the new season, the events for the next few months, and I'll signpost some of the resources that are available from the ASE for those who are not familiar. Then I'll introduce Professor Gibson for our headline talk. And then we have 2 talks internally. We have Mike Christie doing the sky in September, and we have David Brett presenting the image of the quarter results. And he's a previous winner, so he gets the honour of taking us through the latest round of that competition. And that'll take us nicely through to the refreshments. On the subject of images and winners, here's our reigning image of the year, which was chosen by the membership. And this is the Elephant's Trunk Nebula, which was created by Eros Tang. And I'm going to be saying that every time I start a meeting this season, because I think it's a beautiful image and I want to continue to showcase it. So if you want to get your image featured next year, you know what to do. So let me begin this evening with my thoughts for the season ahead, some more details on what we have coming up in the next few months, and a reminder of the resources available. So I said I was going to use the word exciting a lot tonight. It's an exciting time to be an astronomer, and it's an exciting time to be a part of the ASE. And why might I think that? Well, considering astronomy in general, projects like the James Webb Space Telescope, enhancing our space-based imaging and exploration, and the Vera Rubin Observatory doing the same on terra firma, they continue to grab the public interest. And we've had really interesting talks on both those projects as part of the Society. The rapid technical advances in communications in particular means that all this content is readily available. We've all seen the footage of families clustered round a single black and white television in '69 watching the lunar landing. But in 2025, I can live stream launch events and all kinds of stuff onto my mobile device. In summary, the availability of knowledge and data has grown exponentially within a single generation. Now, this is translated to both a group and an individual level. So the availability of knowledge and technology within societies like ours and within the household. That's grown at a similar rate. We've got a vast collection of astronomy equipment in the Society. I mean, you can never have too many, right? But we've got a vast collection. Some of it's miles away in Spain in a purpose-built facility. And some of it's built into a tiny package that I can control with the very same mobile device that I mentioned earlier. And this starts to hint at why it's an exciting time to be part of the ASE. We've now got more than 100 years of history. We're adding to our content daily in the form of meeting recordings, data, images. We're now at more than 200 members, as you've heard already, both locally in Edinburgh and the Lothians and Fife, and remotely. We're running multiple meetings and multiple events every month, and our members' online chat community, well, it's active 24/7, let's just leave it at that. But also our individual competitions, which we'll see in a second, and our project activities are driving creativity and collaborations within the society and making contributions to the wider astronomy community. And the super exciting thing, see I'll use super exciting now, the super exciting thing about all of this is that anyone joining us tonight, whether you're in the room, you're watching on Zoom or YouTube, or you're watching the recording with your cornflakes tomorrow morning, can be part of that. So please, let's all embrace it, the season ahead and beyond. My council colleagues and I would love to hear your suggestions on what we should be doing as a society to keep this buzz going. So coming back to the here and now, what have we got happening this month in September? So in a moment, I'll introduce Professor Gibson for the main event this evening. And then our other meetings this month are our Imaging and Observing online session next Wednesday, which is for members only. And then our mid-month online meeting on Friday the 19th in a universe of auroras. Professor Jonathan Nichols will explore spectacular auroras around the solar system and beyond. Other events this month, we have a collection of open doors events this weekend and at the end of the month. So on Sunday the 7th, there's a gala day at the Collective Gallery, City Observatory in Calton Hill, where we'll be doing guided tours of the Cook Telescope and also promoting the ASE. There's a similar event at the same venue on Saturday the 27th of September, where we will be repeating that. And that same weekend, on both days, 27th and 28th, there's a doors open event at the Royal Observatory of Edinburgh at Blackford Hill, where we'll be doing solar observing. There won't be any clouds, and we'll be able to see a beautiful view. And we'll also be promoting the ASE. So we've got an action-packed September to kickstart the season. Moving into October, our meeting here next month on Friday the 3rd, the two comets, 29P Schwarzmann-Wachmann, thank you, and 12P Pons-Brooks behave like no other. In what way and why? Well, Dr. Richard Miles will describe how, thanks to contributions from amateurs around the world monitoring their behaviour, that we have answers to these questions. Then again, as tradition demands, the following Wednesday we have our Imaging and Observing group. And then our mid-month online session, our guest speaker is Professor Claudia Durham from Imperial College London on the subject of the secrets of gravity. So gravity is the overarching miracle connecting everything we know and the reason the universe itself can exist and evolve. So join this journey to push the limits of knowledge and navigate through the foundations of space-time, underpinning the origin and the fate of the universe and everything in it. Now, you can't miss that. With an intro like that, you cannot miss that. The Saturday after our Friday meeting, we're hosting the joint BAA Comet and Meteor Section meeting in Edinburgh, right here in the AUC. We have an incredible collection of speakers, including our very own Douglas Heggie. Full details about this event, including how to book tickets, are available on our website, which I'll signpost in a moment. And finally, for my look ahead, moving into November, our beginning of the month meeting here, Professor Paul Clark will present a talk on the subject of star formation. The final title will be confirmed soon, so watch this space. Following Wednesday, the 12th, our Imaging and Observing group as usual. And then in our mid-month online meeting, Dr. Darrell Seligman will review the current state of our knowledge of the third macroscopic interstellar object discovered passing through our solar system, 3I Atlas, which was discovered on the 1st of July by the Atlas survey in Hawaii. Now, we don't have anything else planned in November, but after September and October, maybe we're due a quiet month. But one final thing I'd like to add is that you may remember that we were in the habit of encouraging members' presentations at these events. And we'd like to kickstart these again, but we need some contributors. We want to fit them into the schedule, so rather than just a random, right, we'll point at someone tonight, so don't worry, you're free. If you'd like to present something, then please get in touch with Nigel and let him know what you'd like to talk about, and he will fit you into a session. And Mark will put some more details about this in the newsletter, which he will publish, I think he said Monday. Slight delay to this week because he's away for the weekend. So look out for the newsletter on Monday. And coming back to the ASE resources, you can find out a lot more about the Society and keep track of everything that I've just described using this collection of amazing digital resources. Starting with our website at astronomyedinburgh.org, which contains an amazing mix of public and members-only content. Everything from stuff about the meetings, the Imaging and Observing Group, ASRO, our remote observatory in Spain, and lots of amazing historic documentation about our 100-year history. Our YouTube channel and Flickr groups contain, surprisingly, YouTube videos and Flickr images. But there's amazing content, including all of the recordings from these meetings. Our main social media interactions, so just general public chatter, happen on Facebook, Instagram, and Blue Sky using these handles. If you search for Astronomy Edinburgh, you won't go far wrong. And then finally, our two members' communications, the newsletter I've mentioned, and our community in WhatsApp, which, as I say, it's not for the faint-hearted. Blink and you'll miss several hundred messages, but they're all good. Trust me, I read them all. They're all good. So, amazing resources to keep track of what's happening in the Society. So now, after all of that, it's time to focus on our main talk this evening, and it's my great pleasure to formally introduce our guest speaker, Professor Brad Gibson. Now, hold that. Second. There's a big build-up coming. Professor Gibson is an Australian-Canadian astrophysicist. He's the scientific editor for the Astrophysical Journal and has previously served as the head of physics and maths and the director and founder of the E.A. Milne Centre for Astrophysics at the University of Hull, the chair in Theoretical Astrophysics at the University of Central Lancashire, and the deputy head of school at Swinburne University in Australia. Now, Brad's team was responsible for first defining the Milky Way's galactic habitable zone, determining the expansion rate of the universe, and building the world's first liquid mirror telescope observatory. His 1,000+ outreach events over the last 7 years have reached 2 million people around the world, including more than 70,000 students at more than 100 schools and colleges throughout the UK. Brad's commitment to widening participation from underrepresented groups and improving the career prospects of physics students led to his campaign, The Changing Face of Physics, being named best practice in the country by the UK's Equality Challenge Unit. His contributions to science advocacy and research were recognised by his election to Fellow of the Institute of Physics in 2021, and in 2023, Brad was named Honorary President of the Association for Science Education. Ladies and gentlemen, please welcome Professor Brad Gibson.
Thank you for that, Neil, and I will attempt not to disappoint. That's great. Thank you. So, before I launch into what liquid mirror telescopes are and what the concept of a liquid mirror is, which is generally somewhat foreign to most of us in astronomy and astrophysics, who typically have glass and aluminized mirrors in our telescopes and binoculars, wanted to just take a couple minutes to explain how I got to work and develop these sorts of things. It started, well, I guess it really started about 38 years ago. I had to think about the number as I was sitting there. I was finishing up my final year of undergraduate university, thinking about what I was going to do for my PhD. Where was I going to go? What was I going to research? And right around that time, there was an article in, I think it was Scientific American. I guess that was probably like late 87, right at the beginning of 88. And it was all about the search for extrasolar planets, exoplanets. Nowadays, it's still a very hot topic, but we've now discovered upwards of, I think the last time I checked, about 10,000 or so planets in other solar systems around the galaxy. But at that point in time, in the sort of the late 80s, this was a new field. We hadn't discovered anything outside of the planets within our own solar system. And this article came out in Scientific American talking about this group in Canada at the University of British Columbia that had developed a new technique to search and identify planets around other stars. And I won't go into the gory details of how it worked, but basically what it was you took, nowadays when we search for planets, most of the planets that have been discovered, they take picture after picture after picture after picture after picture of a star and look for little wobbles back and forth, or have a planet that passes in front of the star and it blocks a little bit of the light. And so from day to day to day, the star looks the same brightness, and then there's a little dip in the brightness when the planet transits in front of it. And that's how the vast majority of these 10,000 planets have been discovered. But the first technique that was put forward by this group in Vancouver, in Canada, was not to look for dips in the brightness of the star, but to take a spectrum, effectively a prism, a spectrograph, spread the light out of the star, and take picture after picture after picture after picture. Now, if there were no planets around the star, you would see different lines of different chemical elements and molecules. You would see water lines, and you might see carbon and oxygen and iron. And these lines would always be sitting in exactly the same place if there was nothing perturbing the star. But if there was a big planet, Jupiter or Saturn, or a smaller planet even going around the star, it causes the star to wobble a little bit. And so if you take a spectrum and look at these different lines of carbon and oxygen and iron, instead of being in exactly the same place night after night after night after night, as the planet goes around the star, it causes the star to wobble a little bit. And so you see the lines move a tiny, tiny bit, depending on how heavy the planet is going around. And the way that they would determine if the lines were moving very much is they needed something that was fixed. And so what they do is they take the light of the star, comes to your telescope, but before it gets to your detector, your eyepiece, it passes through some extremely poisonous gas, hydrogen fluoride. And so it goes through this hydrogen fluoride. And so you see these hydrogen fluoride lines. They don't move because it's sitting right in front of you. But you see the star lines moving back and forth as the planet goes around relative to these fixed lines of hydrogen fluoride. Got lots of stories about before my university clued in about occupational health and safety. And I was, even though I was 24 years old, I was very naive. And, when my supervisor asked me to, can you just take this suitcase is filled with hydrogen fluoride, stick it in the back of the university van and drive it across on the ferry to the telescope on Vancouver Island. I just did what I was told. I never really thought twice about it. I'm sure it was wildly illegal. I mean, it was incredibly unsafe for me to be just driving around with this incredibly poisonous gas. If I had an accident and this gas had released, it would have caused some problems, including my death, of course. But that's a story for another day. I do have some other health and safety things I'll come back to in just a moment. And so, but this article really caught my attention. It was really, really exciting, and that's the sort of thing I wanted to do for my PhD. I wanted to be on the cutting edge. I was a huge science fiction fan. I wanted to be part of that search and discovery of the very first extrasolar planets. And as I was and that's what cemented my decision to go to University of British Columbia, is I wanted to be part of this search. And the very first paper that was published by this group, Campbell, Walker, and Yang, coincided with the Scientific American article, which outlined this technique that I've just described of how they searched for the little wobbles in the spectral lines to search for these large planets around nearby stars. And this was the first paper that came out from the group, and it was sort of accepted in early 1988 and published later in the year. And they searched around 2 bright stars for these wobbles, indicative of something being there. And that's what they found. They found around one of these stars, if you've got good eyes, depending on where you're looking, Gamma Cephei A, I think it was called. And they found that exactly as I described, the spectral lines of the star wobble back and forth, consistent with some massive Jupiter mass sort of system that was orbiting around close to the star. Now, here's where the problem is. So this was in 1988. Being Canadian, they were incredibly modest. And instead of sort of punctuating everything with exclamation marks, they were very cautious about how they interpreted it. And they said, well, it could be a planet, maybe it's something else. We're not entirely sure. And the problem is they were so cautious about it that it didn't really get recognized that it really was the first detection of an extrasolar planet. And it was in 1995, so about 7 years later, that multiple groups, both in the US and across Europe, actually detected extrasolar planets for the first time using a similar technique, but without poisonous gas as the intervening gas that the light went through. Unfortunately, well, as a Canadian, unfortunately, the group, Michael Mayor and Didier Queloz, they won the Nobel Prize in physics for the detection of extrasolar planets. What they did, though, was confirm the detection that the Canadians did 7 years earlier, because they did go back and look at that particular star that the Canadians had found the wobbles and said, yeah, it's probably a planet, but, maybe hedging our bets, we're not entirely sure. And so it's one of those missed opportunities that the people who were really discovered or really identified and first saw an extrasolar planet, if they'd just been a little more American in the way they presented it rather than those modest Canadians, they would have ended up winning the Nobel Prize. And so that's why I chose to go to Vancouver to do my PhD. I wanted to be part of this process. And I got there and I started my PhD. And after about 2 days of working on it, I realized it wasn't a swashbuckling, exciting search for planets. It was sitting in front of a terminal, doing lots and lots of mathematics, doing all kinds of things called cross correlations. And it wasn't the exciting search and discovery that I thought it was going to be. And so, right or wrong, I can look back sort of almost 40 years later and think, oh, if I'd only stuck with it, maybe in those intervening 7 years, we could have pinned it down and I could have been part of a Nobel Prize winning group instead of the European groups that won it. And so I jumped ship after about 2 days of working on the search for extrasolar planets, not really thinking it was that exciting. Now, I've had a reasonably good career, but it is once in a while it pops into my head, what would have happened if I'd stayed with the search for extrasolar planets? And so what I did was, after 2 days, I walked around the department and spoke to some of the other potential supervisors about what sort of projects they were working on. And what popped up was my eventual supervisor, Paul Hickson, was interested in thinking and developing, building what we call a liquid mirror telescope, which is what I'm going to be talking about in what follows. I didn't know what a liquid mirror telescope was. I didn't know what a liquid mirror was. Obviously, liquids do reflect. You can look in a pond, and if it's nice and still, you can see that the light does reflect off of a liquid, just as it reflects off of a hard mirror as well. But how you would actually do that for astronomy and astrophysics wasn't entirely clear to me. So before I describe how some of the challenges associated with constructing a liquid mirror, let's just take a very quick look at how most reasonably large mirrors are made. And here I'm talking about sort of traditional monolithic mirrors that are one large piece of glass cut into the shape that goes into the telescope. So there is some sound on here. It's not particularly critical, but if you can pick up the sound, that would be great. So here we go. I hope. And the sound is not playing. Okay, but it doesn't really matter. This is how most mirrors are made. You take a big chunk of borosilicate glass, as it's called, and you have a grinder that basically cuts the glass into the right shape, and then it sprays aluminium down, and that's the reflective surface that provides the reflection that you need for the telescope. A new technique that was developed in, I guess this would be sort of in the 90s, 80s and 90s in Arizona, is to put glass, to start with glass, put it into this thing that spins. So instead of taking a hard thing that grinds the glass down into the right parabolic shape, if you like, they put it inside of this container and then crank up the heat really, really high so that the glass melts and it becomes a liquid. And so this is kind of and then what they do is they take this liquid glass and spin it around. And here's kind of an example of what you can do. This is just using water rather than liquid glass. But if you put liquid and color, they put in a bit of green just to help you see the liquid. Just imagine it's liquid glass instead. And you start spinning it around. And you spin this liquid glass, and hopefully it will start spinning. You start maybe with the red color there is to tell you that the temperature is high and it's liquid. And you can see immediately as this liquid starts to spin, it doesn't stay flat. It naturally takes the shape of a parabola. There's nothing sort of magical about that. It was known from the time of Newton, so you can go back, to 1687 to Newton's original work, where he describes the mathematics of why you take a liquid and you spin it around, and it naturally takes the shape of a parabola, which is a traditional shape of many telescope mirrors. And the physics is not particularly important, and you can do this experiment. If you've got a turntable at home and you spin it around, you will see, put some water in a bowl, it will naturally take the shape of a parabola. And it basically comes down to forces that we know and love. You take a flat bowl of water and you spin it. What's happening? Well, gravity is pushing down, because it's always pushing down, and you'll hear more about it in one of the talks coming up in a couple of months. But you've also got what's called the centrifugal force that kind of, as you spin the fluid, it kind of pushes its way outwards. Same thing if you're sitting on a carousel or a roundabout, you spin really fast. Well, you want to hold on because you're going to feel yourself kind of flying off the carousel. And so the balance of those two forces, the gravity pushing down and the centrifugal force pushing out naturally takes the shape of a parabola. And it doesn't matter what type of liquid you are using. It can be water, it can be liquid glass. In the case of the University of Arizona lab that was spin casting these mirrors with liquid glass, they spin it, they get the right shape. If it spins really fast, it becomes really steep. So it changes what we call the F ratio, the F number of the mirror. If you spin it really slow, it has a gentle parabola, so the focal point is much higher up. So you spin it at the rate that you want, and then you allow, and you keep it spinning, 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 and you cool the temperature down until the glass solidifies. And then you spray your aluminum on to give you the reflective surface. And that's how traditional monolithic mirrors are made. With a liquid mirror, the physics is exactly the same. It's just that things stay liquid. And so what is the liquid that we use? You want something to be reflective. You don't want water. Water is reflective, but it only reflects a small fraction of the light that hits it. You want something that's highly reflective. And so what is the liquid that you use? Well, the liquid of choice is liquid mercury for a number of reasons, largely because it is highly reflective and it's liquid at kind of the temperatures that we want to be working at. So where does liquid mercury actually come from? Well, you don't walk out into a mine and find liquid mercury. It doesn't exist in that form. Traditionally, if you want liquid mercury, what you need to do is you go and get a mineral called cinnabar, and there's a little picture of cinnabar there, which is called mercury sulfide. And what you end up doing is you mine this mineral, put it in an oven, crank up the heat really high, which releases the mercury, and then you capture that vapor and you cool it back down again, and it becomes liquid mercury. The vast majority of the liquid mercury in the world, and we don't play around with it so much anymore. I guess some of us are of an age where you, maybe in your initial school labs doing experiments, you may have played around with liquid mercury and pushed it around with your fingers. I can remember doing this 50 years ago, silly things like that. Or you might have had mercury fillings put in at some point in time. The world has moved on. We now realize that mercury is not a great thing to be playing with your fingers or sticking in your mouth. So you might ask, where does the actual mercury come from? Well, the majority of it, 90% of the mercury that is in use, and it is still used in various things, lubricants in particular, high-tech equipment, which I'll come back to. 90% of it comes from China, at least up until through the 1930s, 40s, 50s. It was the mines in China, they used prison labor because they recognized the toxicity of working with mercury. And so prisoners were used to develop the mines that ultimately fed into the mercury that was distributed around the world. So the vast majority does come from China. Mercury, if you've ever played with it, yes, you can sort of push it around. It is highly reflective, as I'll come back to in a second. It's also quite heavy. We normally, you may have had when you were younger, you may have had a mercury thermometer, for example, and that's fine. It's just a little bit of mercury. It's not particularly heavy. But it is actually quite heavy. If you had a pint glass of liquid mercury, it weighs about 17 pounds. These things are, it's quite heavy. It's quite dense, this liquid. And the amount of mercury that you need for some of these telescopes can be substantial. And I will come back to that one in just a second. So mercury, largely because at room temperature, once you've extricated it from the cinnabar mineral, it's liquid at room temperature. So you can use it more or less anywhere to spin it around to take the shape of a parabola. So you might ask, well, how does it compare with sort of the traditional telescopes with the aluminized surfaces? Not that you can see the details here, it's not particularly important, but if you did have great eyes, This just shows you, as a function of time, over a 2-year window, how reflective is an aluminium mirror. And the numbers here, it's roughly about 90%. It doesn't matter if you're using red light or blue light. Light that hits a freshly illuminized mirror, about 90% of that light gets reflected to the detector or the eyepiece. As time goes by, it deteriorates. After about 2 years, you lose about 10%. The reflectivity gets down to about 80%. So for the big telescopes in the world, they do have to go offline every once in a while to freshly illuminize the surface to make them 100% or 90% reflective. By comparison, liquid mercury, if I didn't plot it on there, liquid mercury is about 80% reflective, but it doesn't deteriorate. It stays at 80%. So yes, it's not as reflective as the traditional mirror you'd be using if you've got a backyard telescope or a professional telescope. It will be about 10% lower, but it never deteriorates. Yes, there are things that can impact on that, and I'll come back to that in just a second. For example, dust, or if a bug lands in liquid mercury, it gets stuck and it can't get out. And so, but one of the nice things is you can stop it spinning every night, skim the junk off of the surface and start it spinning up again. So you never deteriorate from an 80% reflectivity. But yes, at its peak, it's always going to be a little bit less reflective than a normal telescope. Outside of mining it, where do you actually get it? Well, you can go online and buy liquid mercury, usually small little ampules like that. I checked this a year or two ago to get the number and converted it to a pint, one of these heavy pints that weighs 17 pounds. So if you wanted a pint of liquid mercury, and I'll come back to this in just a second, but if you wanted to build, say, a 3-meter telescope, a big one, that's about 2 millimeters thick of liquid mercury across it, you need about 25 pints of liquid mercury. So each pint is about 150,000 pounds. So you're looking at something on the order of about 4 million, I think I worked it out, something on the order of about 4 million pounds or so. Now, the project that I was involved with, it was to build a large telescope, this sort of 3-meter class telescope, but it was trying to build it at a fraction of a cost of a normal telescope. Building a liquid mirror telescope is, why would you build one if, picture you've got a rotating liquid, it always has to point upwards, right? If you spin the liquid to make a parabola, you can't point to an object over there or over there or over there. As soon as you tip it over, the liquid's going to fall out. So you're always stuck looking up at the zenith. So unless you can build this telescope at a tiny, tiny fraction of the cost of a large glass mirror, you would never do it. And if it costs 4 million pounds to make a 3-meter mirror, it would cost, if you want to make a 10-meter class telescope, which is what the big optical telescopes are nowadays, that would be about 50 million pounds of just the cost of the liquid mercury. And that's roughly how much it would cost to build the mirror associated with a 10-meter telescope, like Vera Rubin telescope that you heard, or the European Southern Observatory, these large telescopes. That's the sort of number. So again, liquid mercury as a replacement is only a replacement if you can do it at a fraction of the cost, because you do have the limitations that you can't point anywhere in the sky. You can only look at things as they transit over top. So it has to be cheap to be a replacement. So if you go online, this is not the way you would do it. You're not going to spend 50 million pounds to get enough mercury for a 10-meter class liquid mirror telescope. So the project will be dead in the water right away. Or in our case, 4 million pounds to make a 3-meter class telescope. Again, that's just not something that was part of our budget. Our budget was about 50,000 pounds, not 4 million pounds. So we had to think, how can we get this liquid mercury? Well, again, this was a time when I had no idea. I was a fresh-faced postgraduate student who didn't understand what health and safety rules were. And I might have questioned it at the time if I'd been a little bit more clever, but what my supervisor asked me to do was take the van and go to an industrial park at 3 in the morning, which, you know, it should set warning bells off right away. And I pulled up, and then some people came out with 30 or so pints of liquid mercury and put it in the back of the van. No words were spoken, and I just drove away. So this was waste liquid mercury that was used in industry. Again, largely it was used as a lubricant, in places where oil wasn't sufficient. Liquid mercury was a really, really good lubricant. But it has a tendency, you know, it collects dust and junk as it's, you know, working around gears and things. But we could clean that readily. For what they were doing, it wasn't worth their time to filter the dust and contaminants that had got into the liquid mercury. So rather than getting rid of the liquid mercury legally, they just handed it off to us, who took it away. Again, in retrospect, highly illegal, highly dodgy, but again, I didn't know any better. And it didn't cost us anything because we were taking their waste mercury away, so they didn't have to pay to have it removed, and we didn't have to pay anything for it. And we got lots of liquid mercury that was sufficient for the experiment that we wanted to run. This is sort of public knowledge now, so I'm not violating anything by telling you this. And so we collected the 25 to 30 pints of liquid mercury that we needed if we wanted to build this 3-meter class telescope. There was some thought given to what other liquids could you use? And there have been, over the years, a number of other liquids have been suggested as alternatives to the very expensive and nasty aspects of liquid mercury. There are things, other metals like that are highly reflective, like gallium and indium, tin. These are all potential ones. The problem is things like elements like gallium and indium, they are solid at temperatures that we want to work with. They only become liquid at much higher temperatures. Gallium is like 30 degrees centigrade, and indium is much higher temperatures. But there are some clever things you can do by kind of mixing them together. They're called alloys. So you can take gallium and indium and tin and mush them together, and you get this alloy, which is a liquid at the same temperature that liquid mercury is, and it eliminates all of the dangerous, nasty aspects of liquid mercury. The problem is, if liquid mercury is expensive, these alloys, which are safer, are even more expensive. And so right away, any sort of liquid mirror telescope experiment is dead in the water because it's just way too expensive to purchase 25, 100, 200 liters of these alloys. You're talking, you know, hundreds of millions of pounds, and you would just build a normal telescope because it would be cheaper. So liquid mercury is what we went with. Now, we weren't the first to think of this idea of spinning. Like I said, you know, the concept of a spinning liquid taking the shape of a parabola was known since Newton's time. And so there were a number of astronomers who had given some thought to converting that into a telescope. I won't go through all of them. The gory details are all there. It was the first paper I ever published, which wasn't a science paper per se, but a history paper. And I had a number of friends who worked at the Vatican Observatory, so I was able to contact the Vatican and get access to a number of private papers and notes from particularly the first person who came up with the idea of not just making a parabola, but making a telescope with a spinning liquid, and that was Ernesto Capocci. He outlined it in a beautiful series of papers. He never actually built it, but you can trace it back to 1850, the idea people were thinking about making this into an astronomical tool. And again, without going through them in gory details, really the first one that was built was a British astronomer, Henry Sky, who had emigrated to New Zealand, and he built that one in the lab. So there's a nice series of papers which describe the little experiments that he did in the lab to show with this sort of it's only a foot or so in diameter, but it was a beautiful mirror, and he had some great results. The first serious one, though, and I'll show a picture of it later, was Robert Wood in the early 1900s in the US, who did some experiments in the lab with rotating liquid mercury to show you could get a beautiful mirror. But he also put one out into the lab that was 50 centimeters, half a meter or so in size, that he built in his farm in upstate New York, and did some beautiful work with that. But then it kind of languished until Hermano Bora in Quebec, in the French part of Canada, in the early 80s, who revived the idea. And he spent the next 10 years or so really invested in constructing liquid mirror telescopes, and primarily doing it within the lab. And so this is where I came in the late 80s with my supervisor, Paul Hickson. We joined forces with Hermano, building on what he had done within the lab, and we wanted to take it to the outside, where he had a working observatory that actually collected real data, that did real science, using this concept of a spinning liquid. So before I show you some pictures of what we actually built, just some additional challenges that come with having a liquid mirror telescope. And there's things that, if you're doing this little experiment, or the movie that I showed you, spinning the water around, taking the shape of a parabola, that it kind of hides away some of the subtle issues that come into play when you spin a liquid into the shape of a parabola. And there are things that normal hard mirrors don't face. And one of them, and I like to bring this one up, if I was talking to the Flat Earth Society, this was a way to prove, there's lots of ways to prove that the Earth is not flat, but there's a subtle one that you can do, in the sense that, you might think, where we stand here, gravity is pulling us down, right? This line of gravity is more or less parallel to this line of gravity, to this one, to this one, to this one. And, we don't really feel the fact that, the Earth is curved a little bit, and this line of gravity is sloped a little bit more than this line of gravity. Now, if you build a liquid mirror telescope that is, say, of the size, not just a tiny little one, but a 10 meter, 20, 30 meter class, that's still small relative to the Earth, but it's big enough that this rotating liquid notices the fact that we're not on a flat Earth, and the lines of gravity are not all perfectly parallel to each other. And in fact, the Earth is curved, and so gravity lines are not parallel to each other. And so what that does is, when you spin the liquid, to your eye, it may look like a perfect parabola, but in fact, it's not perfect. It gets some spherical aberration. And there's other things. Because it's liquid, you have to worry about things like lunar tides. The moon's moving around, just like the moon sloshes the oceans and the sea around, and you get tides. You get the exact same thing when you get a large 10-meter class telescope. You do get lunar tides that move the shape a little bit. Again, your eyeball may not notice it, but it's enough to introduce what we call coma into the images. And the big one, though, that liquid mirror telescopes have to face, not the small ones, but as you get to 10-meter class mirrors, is something called Coriolis force. And you can picture sort of the Earth spinning around. If you're standing on the outside watching the equator whip around, it's moving at 1,000 miles per hour from your perspective looking at it. If you're standing right at the pole, yes, the Earth is sort of spinning around underneath you, but you're not really moving. And so depending on which latitude you're at, the Earth, where you sit on the surface, is spinning at a different speed. So if you take your liquid mirror, which is also spinning on a little turntable, making a nice parabola, and you plunk it down somewhere on the Earth, at our latitude here in Edinburgh or on the equator, it doesn't really matter. You plunk it down somewhere. What that means is that even though it's maybe 10 meters or so in size, up at the northern bit of the mirror, the Earth is spinning a little bit slower than the southern part of the mirror. And that has the tendency to change, deforms the shape of the mirror, of the liquid. This is not an issue for a solid mirror, but it is for a liquid one. And it can introduce astigmatism and coma at a level which can be actually very significant, this 5 to 10 arc seconds. If you had a high quality mirror in a beautiful site in Hawaii or Chile or something like that, you would definitely see coma and astigmatism associated with the fact that the Earth is rotating. Again, not an issue for for large glass mirrors, but it is an issue for large liquid mirrors. And that's fine, as long as you know going in that that's the case, then you can design a corrector. Light comes down and hits the mirror and bounces back up to the focus, and you just construct a corrector there that fixes it. You can do that. For what we built in this horrific site in Vancouver, where the seeing was awful, we didn't have to worry about that because it was never going to be an issue. But if we were building a large mirror in a nice site, you would have to build a corrector to ensure that you took care of the fact that you've got spherical aberration from the curvature of the Earth, but primarily the fact that the Coriolis force changes the shape of the liquid mirror. So that's one aspect that you have to worry about with liquid mirrors that you don't with solid mirrors. Another one is the fact, like I said, it's a rotating liquid. Whether it's sitting there by itself, not spinning, or whether it's spinning, you can't tip it over. You have to look at the zenith. That's the only thing that you can look at. So you would never build this sort of telescope to study random comets over here, anything over there. It's a survey instrument where you don't care which part of the sky you're looking at. So you look at the zenith, and because the Earth is rotating, right, the objects move across. And so over the course of a night, you can build up a long, thin image as the sky is moving, if you like, over top of your detector. The problem is, or one of the problems is, you can get these beautiful images with by taking a long exposure and not moving your camera, and they look really pretty and they're really cool. But it's difficult to extract some of the science that you might be interested in extracting when you've got these star trails around. And again, with a liquid mirror telescope, it's very similar in the sense that you can't move the telescope to track the objects. You're just getting pictures as these things go across. So you can imagine what the problem is. If I point at any particular point on here, and imagine my CCD is pointed onto this projection on the sky, all of my images are going to be, they're not sort of moving in a nice line across my imaging device, my CCD. They're actually going to be curved. And so this is how we get around, well, we can't actually get completely around it, but what we do is we've got a telescope and we're pointed at the zenith, and we've got a detector, our CCD, that is sitting there. We open the shutter, but unlike what you might normally be used to, where you might point at an object and say, I want to take a 10-minute exposure. And so you've got a nice telescope, you're going to do a 10-minute exposure. So you lock onto what it is you're interested in, and then you allow your telescope to move along with the object as it moves across the sky. Now, we can't do that with a liquid mirror telescope. We're stuck. We can't move anywhere. But you can try and trick it a little bit. Instead of, when you take a picture, you open up the shutter, you move along. So if you like the star that might be sitting in one of the pixels of your CCD, it always sits in the same pixel as you're moving across. What we do with a liquid mirror telescope is you open up the shutter and objects will move across the CCD. So what you do is you take a long exposure, but what you're doing the entire time is you are reading the CCD. So as the object is moving across your CCD, you are reading the CCD out at exactly the same rate that the object is moving. And so the object doesn't get blurred because you are reading it out at the same rate that it is moving. So you try to move the electronics with the object rather than move the entire telescope with the object. And that works to sort of first order in the way that it moves across the CCD. But again, these things, unless you are sitting right at the equator, these objects curve across your CCD. And that you can't get around. So you can read out the object at the same rate that the object is moving across the CCD, but you can't get away from the fact that it's going to be curving across your CCD as well. So you can get really nice images, but they're all going to be blurred with little coma tails that if you're in the northern hemisphere, they're all going to be smeared a little bit to the north. There's not much you can do about it. The further north you are, the worse it is because the curvature is more and more and more. The further south you are near the equator, it's less of an issue. It's just something you have to accept that is there. If you have a large field of view so that you see a big curvature, or if you've got really small pixels, it gets blurred across many, many pixels. Again, not much that you can do about it. You have to accept that that is going to be the case with your images. Now for us, like I said, in Vancouver, where the seeing is, probably 10 times worse than it is in Edinburgh, because it's just a complete nightmare. It was okay. When we took the pictures, as I'll show you, you can't see any of this blurring, but if it was in a really high quality site, you would have to build a corrector that took that into account. So another thing that happens is it's liquid by name, and it's moving as it rotates around. So for the telescope that we built, which is about 3 meters in diameter, you could sort of walk at a reasonably quick pace. You don't have to jog, but it would be a quick walk, and you could walk around the edge of this mirror as it's spinning around. So what that means is that you've effectively got a little bit of wind blowing across the surface. Again, if it's a solid, it doesn't really matter. But when it's a liquid, that little bit of wind as it's sort of moving around at 5 miles per hour, it's just like having a 5 mile per hour wind going across the liquid. And that gives you little ripples across the surface. They're called capillary waves. They're not the big giant waves that you see in oceans, but if you are a sailor, you may have heard of cat's paws, which are the little sparkly the little ripples that you get, which are driven by wind that blow across the surface. And that's exactly what happens with a rotating liquid mirror. If it's just left to spin around in an empty room like this, it's effectively the same thing as having a wind blowing across it. And so as soon as you get little ripples on the surface, the light that would normally come down and bounce up beautifully to your focus, some of it bounces up there, but some of it bounces over there and over there. And so you get scattered light whenever you've got this rotating liquid. Again, one of the issues you have to bear in mind when you're building a liquid mirror. But taking all of these negatives that I've just spent the last 10 minutes talking about negatives, we decided, let's do it. Let's build it anyways. And so the key thing, and I've said it before, it's minimize the costs. We're trying to build the materials. We had about $50,000, so 30,000 pounds, let's say, of materials to build a 3-meter class telescope. So that would normally cost you, 10 million, 20 million, something like that. So we're trying to do something at 1% or 1 part in 1,000 cheaper than you could with a glass and aluminized mirror. Otherwise, you would never do it. So we had to minimize the cost. You also have to bear in mind, you have to minimize the weight, and I'll show you some pictures. This is what the cross section of the mirror looks like. It sits on top of something that's called an air bearing, which is effectively a frictionless, turntable, if you like. It sits on top of that, and it spins around. Now, you don't want to just throw down a whole bunch of liquid mercury, because like I said, it's really heavy, 17 pounds per pint. So what you want to do is make something that is roughly the shape that you want, and then just put a thin layer of liquid mercury on. Because that heavy liquid mercury, it sits on top of this, turntable, which is literally about the size of a turntable that most of us know and love. And so you put that heavy weight on, and it'll flex it, and it bends down because it's so heavy. So you want to minimize the weight and have as thin a layer of liquid mercury as possible. And that means you try to minimize the flexing of this thing. So the way we did it, my supervisor, Paul Hickson, he had a gigantic garage in his place outside suburbs of Vancouver. He had all the fancy equipment to build anything he wanted. He built his own private plane from scratch using, bought his own high density styrofoam, cut it into the right shape. He put the various layers of Kevlar around the wings and the body. So he had experience in building these things and building them to a legal standard that would allow you to fly. And that's basically the same process that we went through. We took what is this high density, very fancy styrofoam that's used for building planes, and we cut that into the right shape. And we had like 8 pi segments that were cut into roughly the right parabolic shape, sort of glued together, and then covered with multiple layers of effectively Kevlar to make it as stiff as possible, but not making it heavy because you don't want it to flex. So you're making it as stiff as possible. And then basically you put it on top of the turntable and try to get as thin a layer of liquid mercury as possible. So that's the process that goes into building them. And Paul had all of the equipment that we needed to do this in his back garden, basically. This is I mentioned Robert Wood. This was one of the first really well-documented experiments. So that's 120 something years ago. It's an interesting, if you read scientific papers now, they're written in a very specific, clinical, almost boring sort of way. There's no self-expression that really creeps into scientific papers nowadays. Very pro forma. If you go back and read his original paper from 1909, it reads more like a travelogue. It's beautiful. He talks about what the weather was like when he left his lab in New York and drove to upstate New York, and what the animals were doing on the farm and all of this. You wouldn't get away with that in a boring, staid paper nowadays. So it is a really interesting read. And he describes the telescope that he built literally by holing out the part of the roof of his barn. He built the telescope in a deep pit down below, and that's where the liquid mercury would sit. And then it sits on not a frictionless air bearing, but as good of a rotating base as he could get at the time, driven with a motor and then piece of fabric that went around to spin this thing that would make it go into the shape. And then he put a camera up here to take pictures of things. And it was wonderfully successful. He was able to look at some binary stars, and he was able to successfully separate them at sort of the level of 5 to 10 arc seconds, which may not sound impressive nowadays, but using liquid mercury built in the deep underground in his barn was incredibly impressive. He moved on to other things and didn't pursue it any further than that, but it is a really interesting and important historical experiment in the field. We didn't build ours underground. It was built in the back garden of my supervisors, Paul Hickson's in Vancouver, just with the silo. It was about, I don't know, 6 or 7 meters tall, the silo. Again, he didn't have any planning permission. I'm not sure what the neighbors thought when this 7-meter silo was being built in his back garden. I came into this project. So anyway, here's the silo. The telescope will be based down in here, the 2.5, nearly 3-meter telescope. And then basically it's a garage door at the top. It's not a fancy shutter that opens and closes like a dome. It's basically a garage door that just sort of slides open when you want to do observing, with a camera up at the prime focus. And we did everything. A couple of other PhD students came along to help out. We dug up the back garden, laid the concrete pad, built the silo from scratch. I am the least handy person you could possibly imagine. I have no idea why I thought I would be good at this particular task. And literally on the very first day, so the very first day I walked into his, his garage is like the size of this room here with all kinds, table saws, bandsaw, all kinds of, but lots of really fancy high-tech equipment for building planes. And the first thing he did, again, without any training, no involvement of health and safety, he gave me these big pieces of 2x4 and pointed me to the table saw and said, cut these down into shape. Now, again, I can't stress enough, I have no skills whatsoever when it comes to handiwork. And I'm standing there in front of a table saw, and I've cut my first piece of wood. That was great. Felt really proud. I went to grab the wood. Of course, I didn't really see the blade spinning around. So that was really smart. And so, stuck my finger in the blade, which turned it inside out. And so within about an hour of starting my PhD with Paul, he was rushing me off to hospital where they had to put everything back together again. And then not too long after that, we started to work on the dome and building that. And this isn't me, but I was standing down here doing some painting. That's me over there doing painting. But I was down on the ground, and guess what? I'd taken up like a hammer or something, and I'd left it up on top of the dome. And it was resting on top of the ladder, and I'm painting down at the bottom, and then I moved the ladder, forgetting that the hammer was sitting up there on top of the ladder, which came down and landed on my head. And this was literally about 2 days before my wedding, and the picture doesn't do it justice. It really, sorry, I should have forewarned you if you have any. It opened up pretty spectacularly. And so for the second time in my PhD, my supervisor was rushing me to hospital to sew it back up again. So all of my wedding photos are all from the front. There's absolutely none that capture from behind. My wife was not pleased by that one at all. After the second time, I realized what I want to do is actually work with the data and interpret the data and sit in front of a computer and a supercomputer and do those sorts of things. I was not cut out to do this sort of thing. But I managed to survive despite violating countless rules of health and safety. I know the university is on top of this now because I did see an investigation that came out after the fact, after I was long gone by this point in time. So despite all of the adventures and misadventures, we did actually build one. And this is it. This was the 2.7 meter diameter mirror that we constructed using the tools and the techniques that I described. And the pictures don't really do it justice. And I was completely amazed by it in the sense that, if you stand, right beside this thing as it's rotating, I mean, you can't tell that it's a rotating, it just looks like a perfect mirror. Yes, you can see the outer parts, the metal bits that hold the liquid in are obviously moving, and you can see some of the components that are moving. But if you just focus on the mirror, I mean, it is absolutely perfect. You cannot tell the difference between an aluminized glass mirror and a rotating one. And you can quantify that in the sense that you can measure just how perfect you like the mirror is. And it's what we call diffraction limited. So when we're in the lab in an isolated environment, it is diffraction limited. And you can do all these fancy tests. The quality of that mirror, 2.7 meters, is roughly the same size as a Hubble Space Telescope. It's exactly the same. They are both diffraction limited mirrors. So that mirror quality, using 40,000 pounds, admittedly some dodgy dealings with the liquid mercury, but we only spent 30,000 pounds, I guess, to make a mirror that was as good as a Hubble Space Telescope in terms of its mirror quality at 1/100th, 1/1000th the price. So in that sense, in the lab, it worked beautifully. And when we took it outside and started to do some imaging, it worked. You effectively get a 2-minute exposure of, if you had, say you had an 8-hour night, and you just open the shutter and you read the CCD out at the same rate that objects are moving over top of you, you get an image every night, which is only 2 minutes in depth, but covers the full 8 hours of sky that pass over. So you get a long, thin kind of shallow image. So a 2-minute exposure with that, you get down to in the red band to 21 in 2 minutes. And as I said, everything kind of looks round because the seeing is so bad there that you don't see the fact that the objects are arcing across the CCD as they're going across the CCD. So again, not something we had to worry about in a site like that. Now you might ask, well, okay, 2-minute exposures aren't particularly great, but what you do, if you wanted to, you could go back and look at the same strip night after night, well, night after night after night after night, take 1,000 of them, and then you would have a 2,000-minute image. You just stack them all up to get deeper images. What you really do, though, is you take narrow filters, not just all the light. You take a filter that's just a tiny bit in the red, and a tiny bit in the blue, and a tiny bit in the green and the yellow, and you can build up what we call a spectrum of the object, more than just a pretty picture. You can look at the different sort of lines that appear. And so we could work out if it was a distant quasar, how far away it was by measuring its redshift. We could measure certain lines that would give us extra information than we would get just from a nice picture. So you could actually start to do some real science with it. The technique that we developed has been picked up by a number of surveys around the world, particularly 2 big surveys using this 3.5-meter traditional telescope in Spain at Calar Alto, are doing exactly the same thing, but with a glass telescope. They can move, obviously, and track the objects. And so but they do exactly the same thing. They change the filter. They have a narrow blue filter one night, and then they choose a filter which is a little bit to the red of that the next night, and then a little bit to the red of that the next night. And so they can build up a spectrum of everything in the sky as they scan around. That was just sort of mimicked exactly what we were doing with the Liquid Mirror Telescope. And just to finish up, I got just a couple slides. Coming back to some of the weird things, I talked about some of the issues that you face with a liquid mirror, Coriolis force, capillary waves, getting ripples. You have to worry about, I didn't really comment it on there, but where we built the telescope in Paul's back garden, there's garbage trucks going by and large vehicles going by. That causes vibrations. Vibrations causes ripples, which means you get scattered light. There's lots of little things that you have to think about. And I alluded to it, right? We now know that playing with liquid mercury, knocking around with your fingers and doing things like that is not a very safe thing to do. And so this was always in the back of my mind, one of the worries. Liquid mercury gives off mercury vapor, and mercury vapor is highly, highly, highly toxic. And so you have to worry about what is you have to have mercury monitors that keep track of what the mercury levels are when you're within the dome, because the dome is sort of confined. Now, you can take one of these mercury monitors and wave it around and measure what is the vapor level. And again, the units don't really matter, milligrams per cubic meter. And you get numbers. When you first start, you pour the liquid mercury on and just measure what the mercury vapor level is, you get numbers up around here, up at these sort of values. And after a few hours of this thing spinning, it settles down. And actually what happens, it's called oxidation. You get this thin, kind of almost like a thin, gooey layer that forms on top of the liquid mercury. It oxidizes with the air. It doesn't affect the reflectivity or anything, but it actually damps down the mercury and keeps it a little bit firmer, if you like. It's not susceptible to ripples and vibrations in the same way. More importantly, it doesn't stop, but it really limits the amount of mercury vapor that floats around inside the dome. Normally, if you're in the dome, you have to wear a mercury mask just to be safe. But after about, the only thing that, the mercury vapor curve is here. So after 3 or 4 hours, the number has dropped down to a level. This is at least up until the 70s, this was the World Health Organization said that was the legal limit, that you could work 8 hours a day It's been recently reduced from 0.05 down to 0.01, those sorts of units. So if you took the old values, after a few hours, you were safe to wander around inside the dome without the mask. Not that any of us would ever do it, but it does stabilize the focus and makes the surface not hard, but relatively hard, kind of gelatinous, if you like, and it does reduce the vapor significantly. Now I sort of moved on. This would have been 1990, 1991. This is like 35 years ago when we constructed it, built it, took the first data, got some papers published showing that you could actually do it, and you could do it at a reasonable price. Weren't able to demonstrate that it would work in a beautiful site with pristine, crisp seeing. There are lots of other issues that you'd have to take into account with correctors that you have to build. So the price that we did was incredibly low, but if you wanted to have a real professional observatory, which took away all of these coma and astigmatism, Coriolis force, all those sorts of things that we didn't have to worry about where we built it, you would have to invest some more money. And so you'd have to play that game about whether the cost-benefit analysis of a liquid mirror telescope versus the traditional approach, but you probably could still come in significantly cheaper than a large 10-meter glass mirror. I moved on into theory and computation and some of the things that Neil alluded to in the intro. And my supervisor broadened out into a number of other projects as well. There were some additional developments, and there are some ongoing developments, but it's not like the community at large has jumped on the bandwagon and gone crazy with building liquid mirror telescopes. I think the limitation of being just a survey instrument that had to point at the zenith, meaning you could not look wherever you want to, just kept people away from pursuing it as a serious instrument, even though you could make diffraction limited, beautiful mirrors. Where it has come into use is in atmospheric research, so not astronomy, but actually studying our own atmosphere and what's called LIDAR. And what LIDAR is basically kind of like in this picture here, you take a laser and depending on the type of laser, you can fire it up and excite different things at different altitudes in our atmosphere. So if you're interested in studying aerosols and dust particulates at different levels, use the appropriate laser to fire things up, and then you look at the reflected light that comes back down. So in that case, it doesn't matter if you're looking at the atmosphere over there, over there, over there, you just look straight up, it's fine, atmosphere is atmosphere. And so a liquid mirror telescope, you just want a big light bucket to collect the light that bounces back down again. And so they're a cheap alternative to an expensive glass mirror, or an expensive glass light bucket. And so we built one for one of the LIDAR facilities in Western Canada that I think it ran for many, many years. I think they've upgraded to something else, but for many, many years they used the liquid mirror to study the atmosphere and the Earth. It's also useful for doing NASA. So NASA caught wind of what we were doing, and so they sent representatives up to see what we were doing with our 3-meter class telescope. They loved it because it was cheap. And so they commissioned us to build a clone of that 3-meter telescope, which they ran in New Mexico for a long time, 10, 15 years or so. They were interested in just studying space debris. And again, when you're studying space debris, it's not so much that they were interested in studying this satellite that's breaking up or this thing that's over here. They just wanted something, again, that pointed at the sky, and they could go night after night after night after night and just look statistically how often is junk passing through that part of the sky. And they could build up a statistical understanding of just how much junk is up there floating around, space debris. It was one of the many different facilities they had in New Mexico and Cloudcroft to study the sky. But one of those facilities was one of our 3-meter class telescopes, this is the one up in New Mexico that we built for them. That again ran for about 15 to 20 years or so, collecting data and mapping out statistically how much junk there is out there orbiting planet Earth. The only other one that's really active right now is there's one in India that my supervisor is part of the team. It's not his primary research nowadays, but they approached him to help in the development of a 4-meter class liquid mirror telescope, which is running in India now. I haven't seen much science. It's worked in the lab and it has been deployed to collect some data, but I've not seen any science papers yet to really pin down how successful it has been. But it is something I'm keeping an eye on, just and hoping that they're able to extract some really good science out of this, what is a beautiful telescope, not in one of the best sites as well. It does have to be said. But that's about it. I did hunt around over the last few years. I dip in every once in a while to see if anyone else has jumped on the bandwagon. But thus far, other than these few little cases, the primary use nowadays really is in atmospheric research. And that was just one of them, but there's a number of groups that are using these liquid mirror telescopes as light buckets for LiDAR, for atmospheric research. That seems to be the primary use nowadays. And I think I don't have any magical, awe-inspiring conclusion other than to say that sort of is a walk through my journey from wanting to do extrasolar planets, deciding it was boring, deciding that liquid mirror telescopes sounded really cool and interesting and I wanted to be involved, being hospitalized a couple of times, deciding maybe theory and computation might be a better way to go. But it's been really interesting for me to develop this talk over the last couple of years because I moved on for 30 years without really thinking about liquid mirror telescopes, but enough people had asked me about them that I thought, yeah, okay, I'm going to sit down, go back through the history, go through ancient photos of mine to find pictures of my head split open, which took me a while. But so it has been a fun opportunity to go back and revisit this little bit of astronomical history, even if it hasn't set the community alight, but it has been an interesting one. And it's nice to know that at least there are a few groups out there still using the technology that we developed to maybe in ways that we had never really thought of before. So that's about it. Other than, one extra picture. I did, my supervisor back in Vancouver, like I said, he sort of kept involved at a small level and helping with the development of the 4-meter class telescope in India. He did build, it wasn't really for science purposes, but it was more sort of a museum piece, if you like, a 6-meter liquid mirror telescope, not in his back garden. By this point in time, the university had said, please stop building things in your back garden. And so they put it in part of the University of British Columbia forest on the side of a mountain, which basically rained like 300 nights a year or so as everything comes in off the Pacific, hits the mountain and drops right there. So it was more of a museum piece rather than an active telescope. But he had a beautiful working 6-meter class telescope, which ran for about 10 years or so, and then it's just been recently decommissioned. But that's really sort of the state of the affairs right now when it comes to these liquid mirror telescopes. And as I said, I don't have any grand conclusion other than to say I hope you enjoyed the journey from where it began to where we are today. So thank you.
Well, thank you, Brad, for a fascinating talk on liquid mirror telescopes with history, physics, health, safety, and DIY included. Yeah. Thank you very much. I think we've got time for a few questions. Perhaps while we're doing that, Mike, you want to get set up. But have we got any questions for Brad?
Hi, thanks for the talk. How wide view can you get practically from a liquid mirror?
Yeah, that's so that one was about. It was only about 30 arc minutes or so, but that was kind of set a little bit by the CCDs at the time as well. We did look at this, and there's other people who have looked at it as well as to what kind of secondary corrector could you build that would open up a much wider field of view. And you can build things that open up 10 degrees or so, Probably the numbers have changed since then, but you could build something that gave you potentially that sort of, even though given the F ratio we had and the CCDs at the time, we were kind of limited to sort of 20 arc minutes or so. But you could have got something that would give you a good quality field of view that would allow you to study a strip, sort of that 10 degrees or so. Now the cost of the secondary would have been, 100 times, much higher than the cost of the mirror itself. So it's kind of a trade-off. It was really pushing the limits of what you could do with a secondary corrector, and it would have, cost X million for the secondary. So again, you start to play the cost-benefit analysis as to whether it was, but you could do it, and yeah. And so people started to think about what other sort of games could you play with firing, having a secondary mirror to push something out somewhere else, and could that actually open up, if you had the appropriate secondary, could you open up areas that were sort of lower down? And so we didn't even think about that, but there are other groups who theoretically thought about this, and you could, as soon as you started to cost it up, you just started to run into, why would you do it as a liquid mirror when it starts to approach the cost of a glass one? So yeah, if you lost it had to be at least an order of magnitude, if not 2 orders of magnitude cheaper, before you'd pursue something that had that kind of limitation attached to it. And the big field of view, and to get down to lower angles, just killed off the benefit of doing it.
Yeah, thank you for that talk. It was fascinating, and I actually was able to follow it, which is another bonus as well. But it's just a quick couple of questions about I don't know what you call it, the dish or the container for the mercury that's going to sell. Is the quality of the surface of that an issue? Does it?
Not really. So what we did, I kind of glossed over it. So we took the dense styrofoam, cut it rough, put metal plates on the side, and then take a hot wire and drag it down to give you a rough parabolic shape. And you do that for, I think we had 8 segments, and you glue it together. And then you cut the bottom off to give it a kind of a wedge profile, again, just to reduce the weight as best you can. And then you put all the Kevlar on, blah, blah, blah. Before we put the mercury on, we actually put this epoxy resin on, and then spin it around at the rotation rate that you want. And then the resin it's not a perfect, you can get little bubbles here and here and there. So it's not perfect, but it's close. You wanted it to be as close to the right shape as possible to minimize the amount of mercury that you needed. So for that sort of epoxy resin, we needed about 2 millimeters thick. If you had it, if you spent more time and were clever about it and got it really perfect, you could probably make do with 1 millimeter thick. But for what we were doing, that was what the epoxy resin did to give you roughly the right shape.
Yeah, and did when the thing's spinning, was there any shear through the thickness of the mercury itself? Did the top of it spin at the same rate as the bottom? Do you know what I mean? Yeah,
I think it initially, when you first do it, yes, but and you can see that partly in some of the measures that they do with how the focal length varies a little bit and things. So yes, but it usually, kind of in the plot that I showed that went up and down, after a couple of hours, it does take a couple of hours. So you start it spinning, and because of the viscosity, the thickness of it, it does take a couple of hours, but then eventually you get almost like solid body rotation, other than the effect of the wind ripples on the top, which people thought, okay, well, you can put a thin layer of mylar over top, and that sort of seals the air inside, so it's rotating at the same time. So there are ways you can try to minimize the ripple effect by using reasonably transparent mylar across the top of them.
Thank you.
Right at the back.
Yes, we've got one at the back,
Can you build a liquid mirror telescope on the moon?
That is a fantastic question. Absolutely fantastic. So people have yes, you can. The short answer is yes, you can. Because there's gravity on the moon, it's not as strong as our gravity. So in the moon, if you try to jump, you could jump a meter, without too much trouble. So if you spin this liquid on the moon, it will do the same thing. It will take the shape. And there's other nice ideas. You could, if you put it on not on the front of the moon that we can see, but if you put it on the back side of the moon, it's really, really, really dark. So you get a beautiful dark sight. So people have actually given some thought. I don't think it'll ever happen, but people have given some thought. If you took a nice sized crater, you could build like 100-meter, gigantic football field size rotating mirror inside of a crater and study incredibly faint objects. And you don't have to worry about wind because there's no atmosphere, there's nothing to breathe, so that you don't get any ripples on the surface. So there are a number of people have written papers about this. Nobody's ever done it. It's not going to happen in my lifetime anyways, but people have given some long, hard thought to it. And that's a fantastic question, really good.
Thanks very much, Brad. My question was very similar to the last question. Is this a sort of technology that could be used in space in a zero gravity vacuum situation?
So there are some papers out there. I admit, as I was coming up on the train today, it popped into my head to go back and look at them. I never bought into I could not envision how you would work this in zero gravity. But there are some papers out there that claim you can do it. I'm not quite sure how it would work. One way, though, that could work, and it would work here on Earth as well. And again, people have done some limited experiments with this. So if you take a liquid, but don't even worry about spinning it, just keep it flat. But what you can do is you can put you can inject different magnetic particles, if you like, into the liquid at different radii. So you have, and you have, powerful magnets underneath that keep everything in place. So little granules that vary as you move out in radius. And so what you can do is you make a kind of a mirror that behaves like a mirror that's this shape, but it's perfectly flat, but it has slightly different reflective capabilities because of the way the particles are injected into the liquid as you move along. And so the light comes down and then bounces back up to a prime focus by changing the configuration of the particles and the density of the particles as a function of radius. So if you could get one of these magnetic granular telescopes, and you can change the magnets underneath, and you can change the focal ratio of the mirror however you want to do it at will. That I can see working in maybe a little bit in space. You've got some liquid and you've got it, at least it's flat. I still can't wrap my head around how you rotate something in 0G and get it the right shape. I don't know how to do that. But I know in the back of my mind, and I meant to look it up, as I said, I was coming up. I knew in the back of my mind that someone had given some thought to this before, but I can't remember the logic on how it actually worked.
Okay, Ian, do you want to unmute and ask your question?
Yes, just wondered if you'd ever tried tilting the secondary to give you a limited form of tracking.
And I'll be here over coffee if you do want to ask me anything.
Or Ramsey, do you want to ask your questions? Yeah, okay, so I'll ask the question. Ian Smith it was asking, did you ever try limited tracking by tilting the secondary?
So no, we did. We kept it very simple and everything was fixed. But I was saying there are some clever optical design people who had given thought to exactly this sort of thing. Not only opening up, being able to go down to lower zenith angles by doing something clever with your secondary or having a secondary mirror, but also doing at least some limited tracking as well. But again, nobody has attempted to do it because it just started to move further and further away from the simplicity of the design. So I think the papers that have been published exploring lower zenith angles and limited tracking with a moving secondary are all sort of theoretical in nature, and nobody's actually done it in the lab. I think theoretically it's feasible, but again, it's right now, everything that I've seen, it's just been a theoretical experiment rather than a real experiment.
And Ramsey had two questions. The first, how many RPM did you spin at?
Yeah, so as I was saying, obviously the faster you spin it, the shorter your focal length gets, so you can adjust the F ratio. For the 2.7 meter, which was a bit less than F2, F1.85 is the number. I don't know, the focal length was about 5 meters, so whatever the numbers are, roughly F2. That was, for that 2.7 meter, I can't remember what the RPMs, can't remember, but it was roughly about 3 miles per hour, 5 kilometers an hour. So it was walking speed. So a brisk walking speed, you could walk around as the thing was going. I looked up just before I came, the 4 meter Indian telescope, what was it? I think it was 8 rotations per, I've got 8 RPM in my head for the 4 meter class telescope, but I don't know what the F ratio was for that mirror, but it's probably a light jog probably to go around that one.
And the second part was, did you have to refocus with ambient temperature change, or did the change in viscosity offset the expansion of the mercury?
Yeah, the variations are not particularly large relative to the variations you get from vibrations. That was the biggest issue that we had. Even though we had what is essentially a frictionless air bearing, which was far and away the most expensive component of the entire telescope, it was still the sort of vibrations from just the environment that were the bigger issue. I don't, and our temperature variations over the course of a night might have only been a few degrees. We didn't do anything where there was going from 20 degrees down to minus 20 or anything like that. The Vancouver climate and the time that we were doing it was pretty steady. So I don't know the numbers off. It's a good question. I don't know the numbers off the top of my head, but I'm going to guess that the behavior on the few degrees level, and I know liquid mercury, it changes. That's why we put liquid mercury in old school thermometers, because it changes. But I think the effect on that let's say a 5 degree temperature change on the scale of what we were doing was smaller than the other issues that we were facing. Again, I suspect if someone went to a diffraction limited space-based environment, yeah, you probably do have to start thinking about having it climate controlled. We didn't worry about having a climate controlled, nowadays fancy telescopes, yeah, they're air conditioned and climate controlled and held at exactly the same temperature all night. We didn't have any of that to worry about. So even if it did change things a little bit, it would have been lost in the noise for what we were doing. It's a good question.
Once again, let's thank Dr. Brad Gibson.
Thank you.
over to Mike to tell us all about the sky in September.
Yeah, it's me to keep you all from your tea, isn't it?
Well, I've got David as well for the image of the quarter.
Yeah. Is this too loud? Okay, so let me talk about sky in September. There's a short version, which is dark and cloudy. There's a longer version, which hopefully is encapsulated. Some of it's encapsulated on this slide, which I stole from our website, showing some of the things that are happening in September. We've got the lunar eclipse that we'll be lucky to see on Sunday. We've got conjunctions, Moon, Saturn and Neptune. We've got opposition of Saturn on the 21st, 22nd. Can't quite read it, I've got the wrong glasses on. And we've got the various other things that are going on. So there's more details on the website, so you're welcome to look at that. What I've done is I've picked up a few of the things. So the lunar eclipse, this is hopefully a clear night, but I don't think the forecast is like that. The totality ends when the moon is sort of 0.3, 0.4 degrees above the horizon. So as it rises, if you've got a really clear eastern horizon, you'll just see the end of totality. As it gets darker, you have the end of the partial phase of the eclipse, which is just before 9 o'clock, but the moon's still only about 8.5 degrees at that time. You'll also see Saturn. Let me see if there's a laser on here. If I get it the right way around, it's probably there, is it? No? Oh, thanks. Okay. Got it. So, yeah. So you've got Saturn near the moon, and the following day it's much closer. And with a bit of luck, that's going to work. Yeah. So the thing that's going to happen in September, which is good, is that the hours of darkness are going to increase a lot. So this, I've got the sunset times, which just after 8 o'clock down to just before 7 o'clock. And what that means is that you've got nautical twilight from sort of 9:30 down to 8:10. Astronomical dark is going to be, it's still about 10:30 at the minute, but by the end of the month, it's going to be 9 o'clock. So what we're going to end up with is anywhere from 5 to 8 hours of astronomical darkness. So long as it's clear, fingers crossed, we'll be able to start getting some good imaging and observing nights. So, what's going on in the solar system? We've got basically most of the planets are early morning objects. So Mercury's low, but it's quite bright in the pre-dawn sky. Venus and Jupiter are very visible in the pre-dawn sky, very bright. Mars is out of view for the whole month. It's pretty much going behind the sun. What we have got in the evening is Saturn. Now, Ron Morley, who's not here tonight, he said he wasn't going to be able to make it, but I stole his picture just before Mark changed the settings that would stop me stealing his picture. I hope he doesn't mind. But this is Ron's picture of Saturn, a great picture of Saturn, which he took the other day. And opposition, 21st of September, but there's also, because the rings are so narrow, because we're pretty much in the same plane, we've got the option of seeing an eclipse of Titan, and we've got a shadow transit. So Titan could be eclipsed by Saturn's shadow on the 12th. It's pretty early in the morning. And the same thing for the shadow transit, which is 5 a.m., yeah, and it'll be through dawn. So that's pretty interesting if we've got that. So what I'm going to do is I'm just going to talk about the night sky, and so hopefully I cover most of what's important without taking us too far away from tea. So night sky, I've gone into stellarium. This is for the 15th at 10 p.m. Or it keeps advancing the time. But can we get the lights down a little bit so this is clearer? So this is looking south. And I think if I do control click on this, I get a, no, I don't get a laser on this one. Okay, never mind. I'll use this laser. We've got, I'm going to have to look at one that's a bit closer. So I don't like turning my back to the audience. So this is looking south. We have M57 up here. We have M27 that a number of us have been looking at around here. So these are things that we can look at. Now, I'm sure there was one other thing I said I was going to talk about. Yeah, that's the most important one, which is why I forgot it. And the key thing that you look at in the summer, fingers too fat, that's what that was. Summer triangle between Altair, Vega, and Deneb, key feature in the summer. So there's a number of things to look at if you're looking due south. If you're looking west, so Mark will be very happy because we've got M13, which, sorry, I keep hitting these extra buttons. Right, so M13 is about here. We've got T Corona Borealis around there, which is never any day as far as I can see. If we look west, we've got, in Ursa Major, we've got M51 and M101 around here, so we can look at that. If we go to the north, we have both M81 and M82, so I'm just kind of going round here, so they're sort of here. For me, that's not really much of an option, because if I was to take a photo from my house, I can just about see Polaris above the roof of my house. So they're not much of an option for me. At this time of year, I have to wait for to the spring. And as we go round a little bit further, we get to what I started the slideshow with, which is M31 here, and M33 is round here. I keep hitting these buttons. So those are just a few things that we have the option of looking at in September. Now, there's been a discussion in the group chat about SmartScope targets. And yeah, I know some people have already started looking at M33. And really, I think there's a couple of options for SmartScopes this month, M31 and M33. Now with M31, with the C star, you're really looking at mosaics. It doesn't cover, you don't have enough wide enough field of view to cover the whole of M31 without using the mosaic function. With the Dwarf 3, you do. And this is a picture that I took at the outreach last January, where we had, is it 400? No, 300 people. There was a lot of people down in Portobello. And I just set the dwarf up half an hour, and that's what we got from Portobello Beach, which is pretty good. So I think the interesting thing, we've found that with the SmartScopes, the more integration time you have, the better the picture. And I'm sure we can do a lot better with both the dwarf, which is that one, C star is that one, that's a mosaic. And one of the things that I was looking at, which surprised me, is you're actually able to pick up globular clusters in M31 with both the dwarf and the C star. If you search for Steve Harrington, there's a guide to the globular clusters in M31, and I started that originally with that picture I had at the beginning, which was taken with a 5-inch refractor, and I was surprised I could see them with that. But actually, if you look at that dwarf image, I've not counted every single one, but there's 6 of them just shown down there, and I'm sure we'll be able to pick up others. So I think something like that, how many globular clusters can we see if we put together a whole bunch of smart scopes, sea stars, dwarfs? Let's find out. So that's really what I decided to cover in this talk. If there's any questions, happy to answer or not answer, depending on whether I know the answer. Otherwise, David is holding you from tea. I've left the power on for that.
Just go over like this. I'll take your glasses as well. Yeah, that's the one.
I don't know if you want to present to a mode or...
No, just display it as they see it, that's fine. I don't have any notes because I'm going to make it quick.
It's up on there, but you can't see it on there.
Yeah, what do I do for next slide then? Just that one?
Just the arrow keys.
Okay. Can folks hear me? Yeah, okay. Right, okay, we'll make this quick and we can all have tea. Loads of really lovely entries this time through, very difficult to pick, and every person I got to help me pick different things. So up until about a week ago, I hadn't decided on this. So we'll fly through them. Lots of submissions, 9 entrants, and yeah, haven't really done anything with them. This one's lovely. It's Dave Harvey's, I think M101 or something like that, with, yeah. With in the foreground a painting is done. I really like this. I really think it would be nice to see more sort of mixed media or artistic stuff coming in. I was actually thinking for the imaging and observing sessions, if anybody is good at sketching or doing non-electronic stuff, maybe 1 month you'd like to give a tutorial on how to do it, because I'm no good at it. I'm certainly no good at painting like this. Okay, this one, Intermarks, black and white entries, really like this as well. Thought it was inventive. I don't know why, but it always seems to be so much clearer when it's black on white. Same with his M81, M82, which looked to me like an old photographic plate. This one, I really like this one. It's really simple, but it's a lovely mix of colours and sort of immediacy. And the clarity in that's lovely as well. And there is a sunflower galaxy. I think that's the Azaro scope. These pictures by Rob of the sun are amazing. I always find his sun pictures amazing. But this one particularly because it's got a real depth to the prominence that's coming over and all the features across the sun. Very interesting to see it in pure black and white as well. And the same here. And this one's fascinating because it's made with a spectroheliograph. So if anybody's in the imaging and observing session a few months ago, we talked about this, and it sort of scans the whole sun in one go. Potentially you could take different wavelengths of light as well, so you get different spectra out of it, different views and different wavebands. And this one, my wife really loved this one. Really artistic choice of colours. Right, I don't know if this will work or not. There we go. It's a lovely movement across there. And a close-up of the same. This is lovely. I haven't really got anything at home that will do a proper wide field view of things, and I look at that and I really wish I had some set up to do it. And here, Brian's got a lovely mix of dust and the galaxies in the background. There's actually in the imaging and observing session on next Wednesday, they'll be going through how to process stuff to really pull out the dust, because it's not something I know really how to do, and an awful lot of detail there that I'm not going to go into. And here, the Galactic Nebula, really like this one, real sort of clarity and cleanness in the single waveband H alpha. And this one, this is Pat and the sea stars. It's M27. It's even got the wings coming out to the side, which I think is remarkable for the smart scopes. But it's like you were saying before, there's a lot to be made out of them if you've got enough people collaborating. And here, a planetary nebula again in dust by Ian. Really like that one as well. I really like planetary nebula, so colourful. And here, fighting dragons. I think I can see dragons there. Certainly, it's a beautiful display of dust. Sort of coming down and coming up. I think, yeah, my son likes that one. And then the ghost of Cassiopeia. That always looks good. Right, and the winner is Brian. Well done. Right, let's get some tea.
Thanks very much, David, for taking us through that, and I'll be in touch with Brian to organise his schedule. Let's conclude the evening with some light refreshment. Thank you very much.